all before I get going. Any questions at all? Yes, sir.
For the 7.2.5, it says like 100 volts for the voltage, but you
RMS voltage. No, it said RMS, didn't it, class?
Yeah.
All right, RMS means you have to multiply by square root of 2 to get the peak value. And the peak value is what's used in Dr. Whitmore's formulas in the book. That's the reason I did that. All right, now the answer in that one for the power radio was wrong by factor 2, by the way. And I put that in the solutions. Did you all see that? All right, make clear on that. Any other questions? Yeah.
On 725, how do we know that lambda is equal to 1? That was kind of...
All right, I got a question about that. You don't, but no frequency is specified, right? There's nothing that constrains frequency. I make whatever, if I make frequency 300 megahertz, the wavelength's 1, right? Lambda 1 is easy because that way beta is 2 pi over 1. It's just 2 pi. That's the reason I did that. And somebody else asked me about that. You did, well, it's a legit question, but here's the trick. In engineering, don't make your life hard. Anytime you can designate something to make the problem easy, do it. Don't make it an arbitrary value. That's my own recommendation. Engineering is tough enough, and really what you're paid to do, if you really want to get down to it, is come up with solutions to problems in the most efficient way possible that is correct. That's really what's going to happen in the real world. That's what you're going to be paid to do. You're not going to be paid to write elegant mathematical formulas to show some and come up with new proofs. You're paid to solve problems in an efficient and accurate way. And I should say cost effective nowadays. But, all right, other questions? All right, here's what I plan to do today, just to give you an update. I know we have a quiz. I would like to go over things that have to do with beam width. How many have heard of beam width before? A couple people. How beam width relates to gain for most antenna systems. I'm going to mention something about patterns for antennas so you'll at least be familiar with it. And I'll mention a few other terms that are common, like the antenna footprint. You'll hear these terms if you're in the Wi-Fi world or if you do anything with cellular networks. Then I'm going to go into monopoles. How many have heard of monopoles? Here's what it is. You have a ground plane. Everything above that ground plane, the current distributions and charge are reflected below it. So you don't need a half-wave dipole. You only need a quarter-wave dipole above the ground plane. There will be an image, and I'll get to that. I'm going to do that. Monopoles. Then I'm going to do array antennas. How many have heard of antenna arrays? Who's here in the military? You are. All right. The whole thing with antennas nowadays, on Aegis class cruisers and everything, they don't have these big, they do, they're called legacy antennas from World War II, revolving parabolic dishes. What they do is they'll have panels of arrays that change the phase on each one of these small antennas, and they guide the beam electronically very quickly with very high directivity, and they're called array antennas. That's the reason we're going to do them. They're extremely useful. They're a little tricky, but they're very useful. And then that will be then the quiz. All right, so that's my goal today. First, we're going to talk about just the beam width of an antenna. Now, when you talk about beam width, it's sort of like bandwidth. It's how wide something is in a dimension that's of interest. So when we talk about beam width of an antenna, usually, not always, if we were to plot this, it's usually not done in the linear domain, but I'm going to do this way. If this was the angle theta, and this was the normalized power density. Now, normalized power density means it can only have a peak value of 1. Y'all with me on that? For any antenna system, I'm just going to come up with 1. And if it did this, this would have a value of 1. By the way, this is about typical. It's a sync waveform that I'm showing you. And there are array antennas that do this. So, right here, this is the angle. And let's just say that this is pi radians, and this is minus pi radians. Usually it's in degrees. Matter of fact, why don't I put it in degrees to make life easy for you? 180 degrees minus 180 degrees. Now, it's pretty evident, I'm saying this is 0, that the main beam occurs at 0 degrees. If we were on the z-axis, that'd be straight up. That couldn't be for a dipole antenna that's aligned on the z-axis. It would have to be for some kind of an antenna that was perpendicular to the z-axis. But a dish antenna has a gain like this. And it will usually not be, yeah, it would be versus angle, but this angle is called the measurement from the bore site, or if you have a dish antenna, it's the measurement from a vertical, straight in the center of the antenna that's going out perpendicular to the area of the disc for the dish antenna. And it's measured this way, and it's not something that's a function of feet, but I don't want to spend too much time on this. Let's assume this has a value of 1/2, this a value of 1/4, just for heck. And say this is 30 degrees. This would be minus 30 degrees. Say this is 60 degrees, minus 60, and so forth. Now here's the terminology. Where most of the power radiates, the beam pattern where most of the power radiates is called the main beam. This is the main beam of the antenna. You all can see it has the largest normalized power value, right? It's 1. And it also, it's dominant. Just look at it. All right, to your eye, it'll be clear. That's the main beam of the antenna. Now, the null-to-null beam width, this is called beam width null to null. We don't usually use this. Would be 60 degrees. You all see it goes to a 0 here, it goes to a 0 here, so the width of the main beam would be 60 degrees. How many see that? Can you all see it back there, far back? That's all it means. Usually you're not interested in that. But I'll tell you why. Usually it's the half power beam, 99% of the time. As a matter of fact, almost 100%. These are called side lobes. Now, side lobes generally are unwanted. You wish we could get rid of them, but you can't. You can reduce them, but you can't get rid of them. And the tighter or the narrower you want that main beam, the more of these little guys that sprout up. It's just a reality of antenna design. You can't help it. So what they do is try to minimize them. And there are tricks to that, and that's in Riggs's antenna course. It's actually quite interesting, some of this stuff. Now, in general, when you look at these things, right here, 90% of the time, the only thing you care about is the width of the main beam, half power beam width, and I'll get to that in a second, and the number of side lobes. That's it. You don't care about the power in the side lobes. You really don't care about a lot of that. You care about this right here. And usually, it's not the null-to-null beam width. The way they usually plot antenna patterns and discuss them, and by the way, as engineers, we look for figures of merit, something to tell us how good something is, right? So the narrower the beam width, the better the antenna in general. It can focus more energy. Remember that. Narrow beam width, good. Broad beam width, bad. Usually. I say that with a caveat because sometimes you want a lot of aerial coverage if you're a cell phone tower and you want to make sure you get a fair amount of coverage in an area. Right? The second thing is this, is the number of side lobes. You count the number of side lobes. And that one I've got a total of 4 side lobes. 1, 2, 3, 4. That's really it. Now what they really look at is this. If this, remember the antenna, I didn't say if it was a dish antenna or how it's oriented. If this is the z-axis and that was theta, what you'd actually see is something like this. Something like this. Probably not drawn this exactly right, but really I got one main beam, 1, 2, 3, 4, 1, 2, actually I got too many. Let me do it this way. I'm trying not to complicate this. Something like that. You follow me on this, class? Now what is this? This is a polar plot where this is the angle theta. Now, a lot of times they'll say it's the angular variation of the normalized power for a given value of phi. Because if you change phi, then this may change. You all hear me on that? Now with parabolic dish antennas, If they're fed with a circular waveguide, they don't change. But if it's fed with a rectangular waveguide, then it will change somewhat. But generally speaking, just appreciate what I'm showing you. Here's what they do mainly. You're going to see this normalized power pattern. It'll be plotted. Try to do this a little better. It'll be plotted in a polar fashion usually. Sometimes they use dB, but it'll be like this. Oops. That would not be good. This has a value of 1. And what they look for is called the half angle power point. If the power is 1/2 there and the power is 1/2 there, they look for this width. And this is called the beam width, but it's the half power beam width. Now, almost always, and I would specify, when I ask for questions, I will ask for the half power beam width in the future. Do y'all hear me? Write it down. I'm not going to ask for the null to null. It doesn't really help. Half power beam width. For an antenna, like a half wave dipole, that thing is massive. It's over 90 degrees. It's about 90 degrees, which is horrible for any kind of focusing. For any kind of a target acquisition radar, like used on an aircraft carrier or out at Atlanta Airport, where they want to be able to single out an aircraft, find its range and its velocity, that's maybe 1 degree to 2 degrees. Sometimes sub-degrees, all right? Very narrow band. Think of a flashlight and shining a flashlight at night at things. Right? If there's a whole bunch of things out there at night, I don't know, say you're looking at kids in the yard. Well, if you got a big searchlight, yeah, you illuminate them all, but you can't designate one. You get a small flashlight that's got a fairly narrow beam, a police flashlight, right? You can shine and it'll be right on the kid's face. You can pull him out. That's what you want, right? That's the kind of thing you want. And that's the best analogy I can come up with. Right? But you want to make sure, I mean, the ideal is when you have target acquisition radars or radars that are meant to locate, designate, and then track targets, you want very narrow beam widths. In the nautical world, where you marine navigation, they want very narrow beam widths in the actual plane of the surface. Like they would like to have sub-degree beam widths as they scan around the surface. They don't care about the vertical beam width because frankly, who cares? If you're looking for navigation on a sea, you don't care if there's a plane at 30,000 feet. Y'all follow me? Those are called 3D radars. You just want a very narrow beam width along the surface of the sea. These are just things to consider. And we don't go into this too far. So that's beam width in a nutshell. A simple calculation of beam width to bring this out. We know the normalized power pattern for a short dipole is just the sine squared of theta. Y'all with me on that? Now this is a problem. I gave this to you a couple lectures ago for homework. I wanted you to just become familiar with this. Are you with me on this, class? That's what it is. If we take a look at the beam width of this, and I'm going to plot it in polar coordinates. So this would be the z-axis, this would be the angle. It would look like this. Right? And again, this is the measurement theta, and this is the actual length of the range vector r. Y'all follow me? That would be sine squared. How many understand what I've done there? With me? All right, what's the beam width of that? Well, first locate where the maximum is. Y'all see how the maximum occurs at 90 degrees, class? How many? You got that? It's sine is 1 at theta 90, right? It means this is a right angle, and this would be a value of 1, right? Now, if that's the peak value, half of that value would be the half power point. Y'all follow me? Which would be 1/2, right? All right, sine squared equal 1/2 would be for theta equals 45 degrees, right? Because it would be the sine of 1 over square root of 2, which is 45. Y'all agree with this, class? Your calculator, you can do the inverse on this if it's a funky thing. So we know that if we're at 45 degrees here, that power point is 1/2. And also, where's the other point? It's symmetric from here. It would be 45 degrees from here, or at 135 from the actual from the z-axis, right? This would be 135 degrees. And this would be 1/2. Y'all follow me? So what's the angle between this point and this point? Just look at it. Well, it would be 135, right? Minus 45 or 90, wouldn't it, class? How many see that? And that's horrendous as far as gain. So that means this has a half power beam width equal to 90 degrees. That's really bad. I say that. I'm a radar guy. I don't need broad things. I need very narrow beam patterns to track targets. Now, here's something. I don't really focus on causing a grief with this. I just want to make sure if I give you a simple pattern, I gave you a sine. What if I gave you a cosine? What would it be? Just think about it. All right, first draw the pattern. If it would be cosine squared theta, and remember, theta is measured from here. Well, what's the cosine of 0? Right? So it starts at 1, and what does it do? Goes to 0, right? And this would be at 90 degrees, and then what happens? It starts going negative, but since it's squared, it does this, right? Y'all with me on this? This is not an exaggerated drawing, but y'all follow me? So where is cosine squared equal to 1/2? It's where cosine equals 1 over square root of 2, or at, y'all agree 45 degrees? Everybody's suspicious. I don't want yeah, sure, it's 45 degrees, right? That's what it was last time. What's the difference in this one? It's on. Yeah, it's not shooting out it's not at 90 degrees, it's at 0 degrees, right? So what's the beam width? It's from here, right, to here. Now here's the thing that bothers people. You're going to say, but the measurement always starts at 0 and it goes to 180. It doesn't go to 360, right? When you're talking about beam width, you're talking about in the physical world, where is it? If this thing, basically you can take this thing and spin it around the axis, right? It would look like an ice cream cone with a height of 1/2 there, right? Y'all with me? Minus 45, think of it that way, to plus 45. Yes, it is 90 degrees. Do y'all see that, class? How many see that? Now, I can come up with screwy patterns, but if you can draw them out, sketch them out, you can always figure out where it's a maximum, and you can figure the beam width from there. And I don't try to cause you grief. Fair enough? Now, let me tell you one other thing. And what I'm about to tell you is only true for high gain antennas, but it's valuable. I'm going to put it right here. It has to do with using beam width. Most antennas, when they're designed and built, and I have come across this in my own life, every type of a designer, he believes his construction that he comes up with will be built exactly the way he designed it. And that is a big, dangerous mistake, and I've made it. I made it for a lot of money. All right, so I designed an antenna that was 3 arms with multiple small antennas on it, and it was for a synthetic aperture radar. Long story, long time ago. Right? So the drawings got shipped off and were built by a separate vendor. This was for NASA. I didn't have the power to just do it, and I wasn't there. When you go to a vendor, they have technicians that solder things. These are not electrical engineers that have radar or anything like that. They're just people that work there. And they don't inspect the work per se. So it goes out to Ball Aerospace for testing. And when they tested the antenna, the guy calls me up and he says, you know, that antenna's got a standing wave ratio of 4 to 1 on it. All right? A standing wave ratio is 1 is acceptable. 1.1, okay. 1.2, anything over 1.3, 1.4, somebody messed up. When it's 4, it's like a moron design. You can't get any worse. I'm there, are you kidding me? He said, no. So he started ripping it apart. I get a call back and goes, I found the problem. You didn't build this, did you? No, I didn't. Somebody left a solder ball about a ½ an inch large, a ½ an inch in diameter, on the actual input feed. Now what happens is they have to solder coax line into things. A ½ inch diameter solder ball is a giant inductor, and it was at a 1.4 gigahertz frequency. So he goes, do I have your permission to get rid of that thing? Yeah. He was an engineer. He really was. Got rid of it and worked seamless. But that's my story about don't assume your design was built to spec and works if you can't be there. This is personal to me because I thought I was going to lose a lot of money. Anyway, back to this thing. Here's an approximate way to get the gain, maximum gain or directivity for an antenna. D max, and this is only for our narrow beam antennas. Well, really, they're for target acquisition radars, but you don't have to worry about that. So what's a narrow beam? Theta of the order of 5 degrees or less. And this calculation would be in radians. D max would be 4 pi, and you're used to saying it's over the integral, right, of the normalized power density times the sine of theta times d theta d phi. And that goes from 0 to pi, this goes from 0 to 2 pi. Do y'all remember that? That's just the definition of D max for an antenna. Now the truth is this. This really is 4 pi times the half power beam width in the phi direction times the half power beam width in the theta direction, where both of these measurements are in radians. And that's very close to the actual directivity maximum. Now that's a cheap way, it's a very easy and effective way for a guy to do some measurements in an antenna chamber and not have to measure the whole thing everywhere, all the pattern to do this calculation. He just finds the beam widths and the beam width for the main beam, half power beam width and theta and phi, and he's got that. But these things are in radians and they're small, very small numbers. Got that? So these are high gain antennas, things with high D max. All right? I want to just throw that out there. It's not Wentworth's book, but I know from my experience and in radar that's important to at least be introduced to, because some of you, I don't know how many of you, but some of you are going to be working around antennas that are high gain antennas for a lot of reasons. Now, something else I'll tell you. In the wireless world we live in, quote, coverage is important. You've heard that term. Wireless antennas are used, I can't say always, but a lot of times are patch antennas. And when you have patch antennas, they want to get at least a fairly broad beam over an area. So if you have your cell phone, you'll get it, right? So now some of the smart antennas actually locate you, then they single you out and track you, right? But that's advanced. So they get what's called an aerial footprint. And an aerial footprint means they don't talk about beam width. What they do is talk about the coverage on the ground in square meters of the antenna. You can convert what I've talked about beam width into that, but it depends on how far away you are, and it's basically trigonometry. I don't even mess with that in this class. I just want you to be aware of it. It's usually in square meters of coverage area for an antenna. Anybody here in Wi-Fi, or do Wi-Fi work at all? Anything with any cellular towers? I had some experience with this years ago, and I was working with Adtran, but I can tell you that's a big, big deal. Making sure they have cellular coverage. Down here, it used to be your cell phones didn't work. Now they do. All right, my cell phone just lit up, by the way. So that's the reason I mentioned. Most of you get cell coverage down here? Mm-hmm. They didn't used to. All right. There was a need, so they met the need. Probably with towers, repeater towers around the area. I'm not really sure. Okay. Now, after that, we talk about monopoles. This is the one part where it's going to make sense to you, but you don't need to take a lot of notes. You just have to sit back and listen, because this stuff is Imag 1-ish. All right, now we're talking about monopoles. Well, mono, one pole. It means that there's really going to be only one half of the antenna that's used for these. So, first you go through a little lesson in imaging. Imaging of charges. I don't know if you get this in EMAG. How many had me for EMAG 1? You did. Did we cover imaging? You don't remember it, Willie? I think I usually touch it. You did too. I know you had been. But the truth is, it's a very powerful technique. Now here's what happens. When you want the electric fields out here, or the voltage, you don't really care what kind of mathematical solution you use as long as it's accurate. You could care less if it's differential equations, if it's Bessel function expansion. You want the answer. So here's what happens with images. This is going to be a good conductor. Down here, this is a ground plane. Good conductor, that's all you need to know. And if I have a charge right here, a charge Q, and it's at a height h, let's make it a positive Q. If you were to use that and solve for, say, either the E field, the electrostatic E field, or the voltage out here, that'd be a very difficult problem, and here's why. Because this positive charge would induce negative charge in the ground plane. And you'd have to know that negative charge's actual profile, and then calculate the electric field from not only that, but all that negative charge. And it's a pain. Y'all follow me? And you would have to solve a differential equation, a Laplace equation. But a method you can use that completely circumvents that and is mathematically identical is take an image of this charge and stick it at the same length away from the plane, h. In other words, you're going under as far as you went up, and you make the charge negative q. All right? So whatever was positive becomes negative. And then you say, if I wanted, say, the electric field here, you would find the electric field from the plus charge, and you would add it to the electric field from this negative charge. This would be R negative. And you get the total electric field. Y'all follow the thought on that? Now you completely forget about the ground plane. And you would look at these as 2 point charges. Y'all remember point charges are easy to deal with in terms of the electric field and voltage, right? Now, no differential equations, no pain in the butt. And that's mathematically equivalent. It's an exact solution. Y'all got me on that? It's called images. Positive up here, negative below, same distance. So how does that work with currents? Please watch this. This is important, you see it. So here, if I have a current, this is the ground plane, and I have a current moving in this direction, I, parallel to the ground plane, and it's at a height h. I'm just drawing a current. What actually is happening when you have current is that positive charge would be accumulating there, and negative charge, in a sense, would be accumulating there. You're pushing positive charge that way. That's what I'm getting at. Y'all agree with this, class? Now, if you have negative charge here, if you go a distance minus h here, that would image as positive charge here. Positive charge here, it would image as negative charge. And you can see that the image of current that would be developed, here current's flowing this way, this current would be flowing this way. Y'all see that? The point I'm making is that if you have a ground plane and you have parallel, if you have current above a ground plane parallel to it, it's got to be parallel, it images in the opposite direction below the ground plane. Now if you wanted to know the total electric field out here somewhere, you would find the electric field from this short little dipole or from this antenna system and add to it the electric field from here. A point I should make is these fields only exist above the ground plane. They do not exist below the ground plane. Y'all with me on that, class? This is only as a method to get the solution above the ground plane, but nevertheless, it is a solution. Y'all follow me? All right, what about if currents are vertical above a ground plane? So here's a ground plane. And now I got this. And I'm going to say this is a height H1, right here, the lower height. And the length of this is L. Well, how do we deal with that? Same way we did before. Where the current's going on top here, this is going to be a positive ball of charge. Where the current's coming from down here, this is a negative ball of charge. Got me on that? Now image those charges. Negative goes down a distance h and becomes a positive ball. The positive here, now I go ahead and extend this a distance L down here. And the positive becomes a negative Q. And can you see that really this is like imaging a charge where the current would be in the same direction if they're vertical to the ground. Y'all see that, class? How many see this right here? Now, I'm saying that because what does that really mean in terms of an antenna system? It means this. If I have an antenna, and instead of putting a half-wave dipole, let's make this thing lambda over 4 in length. All right? And make that a ground plane. This is called a quarter-wave monopole. Well, it would have a current on it, but the current would be in the vertical direction, I, right? And it would image the other half of the antenna, right below that ground plane. This image would have a current I below it. It would be a quarter wavelength long. And guess what? Because it images down here, it looks like an actual lambda over 2 dipole. Y'all follow me? Now the total fields out here at some distance r, some distance theta, would be the same as if it was a half-wave dipole, but there's one condition. You have to know what the current is right there. All right. So the electromagnetic fields out here at any distance r would be the same if it was for a quarter-wave monopole as if it was a half-wave dipole with no ground plane. You all with me? You have to have a ground plane. If you know the current. Now here's the thing. I want you to know this. I want you to think about this. If the fields are the same for a given current, just hear me. The radiated power would be the same if it radiated over all space, but it doesn't radiate below the actual ground plane. Y'all see this? So exactly half the power is radiated in a quarter-wave monopole compared to a half-wave dipole because it only radiates in the upper plane. Y'all see that? Which means the radiation resistance is exactly 1/2 that of, because the power radiated is 1/2 I naught squared R squared. If I naught is the same, R is the only thing that can vary. The radiation resistance comes down by a factor of 2. Do y'all follow me? So, if you have a quarter-wave monopole, then R rad is really 73.2 over 2, which is about 36, I think he does it 36.5, something like that. You can check that. He's going to have about 36.5 ohms. Now, that's useful information. Another thing that happens too, and I got to just mention this and I'll give you a quiz. When you have this, if you think about the directivity, just the formula, and I'm going to mention this. Remember I told you the radiation resistance goes down by a factor of 2? Well, directivity max is what actually, you don't need to write this down, I'll give you the bottom line in a second. I know it's 4 pi over the integral from 0 to 2 pi over the integral from 0 to pi of the normalized power density times sine theta d theta d phi, right? And I know if it is a half-wave dipole, this d max would be equal to 1.64, right? Now, hear me. If the current is the same on both, I mean, really, you're going to talk about normalized power, so it becomes an irrelevant point. You want the angular variation, correct, class? Well, since the angular variation for the monopole or the dipole, half-wave dipole, quarter-wave monopole, are the same, P normalized is the same, right? But what changes? We don't radiate from 0 to pi. We radiate from 0 to pi over 2 or 90 degrees. So the actual D max doubles for a monopole. So for a monopole, this is for a dipole right here. This is a lambda over 2 dipole. D max would be twice that, or 3.28, and that would be for lambda over 4 monopole. I don't really worry about that, because really I know when I'm dealing with a monopole antenna, it's just like a dipole. The only thing I need to do is find the current feeding it, okay, and I got the answer. That's really it. I've got the E field or power radiated, whatever I want. That's the bottom line. I'll give you some problems on that. That's what I wanted to do. All right, now you're quit.